stress-strain relationship. Let's see. The stress-strain relationship of soil and the cyclic dynamic load has two characters. We all know that for soil, the behavior is non-linear. Then, under cyclic dynamic load is also a non-linearity we can find. And hysteresis, because the load is a cyclic load, then there's an unloading and a reloading process. Then the stress-strain relationship of the soil also have these properties. The hysteresis have a unloading branch of stress-strain relationship curves and the reloading stress-strain relationship curves. And the hysteresis loop reflects the hysteresis of strain on the stress. And the unloading branch and the reloading branch totally create a loop. Then we say it's a hysteresis loop. And the backbone curves reflects the nonlinearity of dynamic strain. In the different strain level, then they have the different stress response, or we say in different stress they have a relative strain, and the strain level, strain status will affect the slope of the loop, hysteresis loop. The combination of two reflects of the whole processes of the stress-strain relationships. Let's say there's a two branch, unloading branch and a reloading branch. In order to simulate the stiffness and the energy loss of the soil, the slope and the surrounding area of the hysteresis curves corresponding to strain amplitude should be equivalent to the act value. Now, if we create a relationship between the stress and the strain, and because we have an unloading branch and a reloading branch, and create a loop, and the area inside the loop represents the energy loss in this cyclic load in one cycle, and the amplitude of the area depends on the amplitude of strain. And if we make a model, and this model can draw a hysteresis loop, and this model can be used or not in practical engineering, depends on the area inside the loop is equal to the actual value or in situ practical engineering value or not. If the area close to the actual value, then this model can be used. Now let's see definition of equivalent viscoelastic dynamic deformation parameters. We create a model, And then this model can use a viscoelastic model to describe it. And perhaps it's not only use viscous element and elastic element to create this model, but we can use the viscoelastic dynamic model to describe this. And for this viscoelastic dynamic model includes some parameters. And for any model, we can use these parameters to describe it. Because this model perhaps is not a real viscoelastic model, then we say it's equivalent parameters. Now let's see these parameters. The first one is second modular, and we use G as its subscript, means second. G second is equal to tau C divided by gamma C. Tau is the shear stress value at the end of unloading branch or reloading branch, and gamma C is the strain value in the end of one branch, unloading branch or reloading branch. Then this value is used to describe the average slope of hysteresis loop. Another one is tangent modulus, and we use subscript T here. GT means G tangent. It's calculated by dt divided by d gamma. And this dt is a small increment of shear stress. D gamma is a small increment of shear strain. In fact, this is a derivative calculation. And we use this value to describe the instantaneous stiffness at each strain. In fact, for hysteresis loop, we can find 2 ends of them, ends of unloading or reloading, two ends. And if we connect these 2 ends, this straight line will through the original point O, 0. Then the slope of this straight line is just the second modular, or GS, and we use this to describe the average value, average slope of the hysteresis loop. And tangent modular is any point in the unloading or reloading branch, any point. We draw a tangential line, and the slope of this tangential line is just tangent modulus. And this slope, or this value, is just instantaneous stiffness at the corresponding strain. The third one is damping ratio. And let's see how to calculate the damping ratio. In fact, we already introduced many times. The area of the hysteresis loop A, B, C, D, A, the area inside hysteresis loop represents the corresponding energy consumption. This is a loss and energy loss in one cycle of cyclic load. And we use A to describe it. A is the area of hysteresis loop, The ratio of energy consumed by soil in one cycle of cyclic dynamic load to the potential energy corresponding to the maximum shear strain in the cycle is called the damping ratio. Here, this is the damping ratio. In the dynamic traction test, the following formula is used to calculate the damping ratio of the soil. Just use this equation. And in this equation, we do know what is A and what is L. L is the area of the triangular COM, which represents the potential energy stored in the elastic soil when loaded to the stress amplitude. Is elastic potential energy. This area. Then we do a cyclic dynamic traction test. Then we can create the hysteresis loop. For each loop, for the loop, we can calculate the area of the loop and calculate the potential energy, elastic potential energy, COM. Then we get A and AL. Then we use this equation, we can calculate the damping ratio of the soil. And this based on a traction test result. And let's see the maximum shear modulus, Gmax, and Gmax equal to G0. What's the G0? In fact, G0 is just the initial shear modulus. The slope at the origin of the skeleton curve's coordinate. For example, 0 cyclic shear strain. Shear strain is 0. Represents the maximum shear modulus, which is called the maximum shear modulus, also known as the initial shear modulus, because it is the start point of bone, the bone curves. Then is the tangential line is just the initial shear modulus of it. And in fact, with the development of strain, the slope will decrease. Then the initial value of the shear modular is the largest value, and we define it as maximum shear modulus. In the experiment, the shear modular under the condition of small strain can only measure and replaced by it. Since the shear strain produced by large series of seismic geophysical experiments is generally less than 0.0003. The measured shear wave velocity can be used to calculate Gmax. You see the here is said that the seismic geophysical tests is under the condition of very small strain. Then for backbone curves, this is very close to the original point. Then we can use the seismic geophysical test to get the maximum shear modulus or initial shear modulus. The equation is given here. Gmax equal to rho times the Vs square. And rho is the density of the soil, and the Vs is the velocity of S waves. The measured shear wave velocity is usually the most reliable means to evaluate the in situ values. We usually we will use this method to get the maximum shear modulus in situ. Let's see the Hardin and Black's method. Soil modular G is related to average effective stress sigma m prime and water ratio E and shear strain gamma and the time effects of secondary compression T and shear history H and loading frequency F and particle character C. Particle character C, and the soil structure theta, and octahedral shear strain, and the saturated degree S, temperature T. This relationship is present as G, shear modular, is a function of all these factors. Here I explain that the time effects of secondary compression is because in the soil after consolidation the effective stress will not change. In this condition, the strain will go on develop is very, very slow. We define is due to the creep, C-R-E-E-P, creep properties of any material. Then in this deformation in soil defined as secondary compression. And this secondary compression will cause the soil tend to hard. Then the time effects, the time will affect the stiffness of the soil. And the shear history is in the history the shear the stress parts of the loading and different stress parts will cause the different deformation. Then we use H here. Our loading frequency, the loading speed will affect the deformation or the stiffness. Then we use a frequency to describe the velocity effects. The particle characters are C. Usually this is for smooth round particles. The stiffness is different with that of sharp gravel soil. Then we use C here. The soil structure theta here. In a certain time, the soil will create some structures. What means structures? We know that in the soil there's chemical materials, and in a long time, this chemical material will create the cement between the neighbors particles. Then it will create the structure in the soil, and this structure will make soil tend to hard or have higher strength. And octahedral shear strain is a kind of description of the stress state. Then scientists find that this shear strain will affect the stiffness of soil. Another is the saturated degree. We use big S here. This will affect the stiffness of soil. And temperature will also affect the stiffness. Then in fact, G shear modular is a function of all these factors. However, when the shear strain is less than 0.0001, other factors except sigma m prime and the water ratio E have a little influence on the cohesionless soil. Sigma m prime is the average of effective stress, mean value of effective stress. E is water ratio. For cohesive soil, the influence of over consolidation ratio should be considered. We know the soil divided into under consolidated soil and normal consolidated soil and over consolidated soil. Usually, the normal consolidated soil will have large deformation, but for over consolidated soil, the deformation is not so large, right? Then the consolidation degree will affect the stiffness of soil. And we use OCR. We use OCR, over consolidation ratio, to describe the degree of over consolidation. Then usually in the equations should consider OCR, over consolidation ratio. Or do you remember how to calculate OCR, over consolidation ratio? It's just equal to PC divided by current vertical effective stress. This is a ratio. Then what is PC? PC is the in previous history the largest consolidation stress. We define it as PC. Or we say it's a pre-consolidation stress. Now let's see. Hardin and Black propose equation to determine the maximum value of shear modulus. Is equal to 625 times a function Fe and times OCR powered by K, and PA is a unit term. PA is air pressure. Then times the sigma m prime divided by PC powered by N. Here let's see, a function f is a function of water ratio, and k is the index if over consolidation effects, which can be calculated using plastic index and use table proposed by Hardin and Black. Here, this is the table. If we know the plasticity index, we can find how much is K. In this table. And the function of Fe, Hardin proposed equation in 1978. Fe equal to 1 over 0.3 plus 0.7 times the E square. And another scientist, Jamil Kawaki, also proposed another equations in 1991. F equal to 1 over E point 1.3. The modulus index n can be obtained by fitting the test result and the different means effective restrained pressure. Generally, the variable range of n is from 0 to 1, which is usually taken as n equal to 0.5. Hardin and Richard obtained the following empirical relationship through the experimental study, or for round clean sum, and the condition water ratio E less than 0.8. They proposed this in 1963. Here we have three equations for Vs. Vs is the velocity of S wave is equal to 170 minus 78.29 times E, then times the sigma m prime powered by 0.25. We also have other two equations, but this is a different unit, just different unit. For example, the first one is used kilogram. Of the second equations use pounds. And for Gmax is 2,630 times the 2.17 minus E square divided by 1 plus E, then times the sigma m prime powered by 0.5. For clay, besides sigma m prime and E, the influence of over consolidation ratio cannot be ignored. Then we have to use a term of OCR. At this time, Gmax equal to 3,230 times the 2.97 minus E square divided by 1 plus E, then times the OCR powered by K and times the sigma m prime powered by 0.5. For special soil types, different empirical relationships are suggested. For example, for sand, seed and egress in 1970 suggested that the following formula be used to estimate the maximum shear modulus. Gmax equal to 1,000 times the K2 max times the sigma m prime powered by 0.5. Here, K2 max is determined using a water ratio E or relative density dr. The empirical relationships are given in the following tables.